Chapter 2, Multi-Detector CT Data Acquisition. Volumetric imaging in multi-detector CT requires routine acquisition of high-resolution data sets. The difference between single-slice CT and multi-detector CT is in how the data is acquired and then how the data is reviewed. With single-slice CT, there's little difference between the slice thickness that the images are acquired at and the thickness in which they are reviewed. Volumetric MDCT is different. There is a major difference in how data is acquired and how it's reviewed. Data is acquired in very thin data sets that are used to generate thicker axial slices, as well as multiplanar and volume images. The goal of volumetric imaging with MDCT is to acquire data sets with isotropic or near isotropic voxels whenever possible. Now in single-slice CT, voxel is longer in the z-axis than in the x or y, and this leads to poor quality images for MPR and 3Ds. But in MDCT, an isotropic voxel is created. It is a cube measuring the same in x, y, and z planes. It allows for true 3D imaging with no loss of resolution. Now, there are two different types of variables when you are doing a CT scan. The first type is the scan acquisition variable, and those are the variables that determine how the images are acquired. The second one is reconstruction variables, and that determines the presentation of the data or how it's viewed. Now the scan acquisition variables that we will be covering in this chapter are scan mode, slice number and thickness, helical pitch, field of view, rotation time, radiation dose parameters, and scan length. The different data reconstruction and viewing variables are reconstruction thickness and algorithm and multiplanar reconstruction. We'll cover those later. Let's get started on the scan acquisition variables. First of all, let's start off with scan mode. There are two different kinds of scan modes: helical, which is also called spiral, and sequential, which is also called axial. Helical is preferred for almost all cases and is essential for volumetric imaging. Sequential is used for brain and coronary calcium scoring when performed in conjunction with prospective gating. It allows for sharper images with fewer artifacts. Next we'll move on to slice number and thickness. MDCT has limited fixed number of slice thickness options. For a 16 slice machine, there's 0.5 millimeters to 0.75 millimeters for the highest z-axis resolution. There's also 1.0 to 1.5. Now you'll get faster table speeds, but you're going to get lower resolution. The bottom line is we need to choose the highest resolution setting that will provide the coverage needed in an acceptable time frame. Next on our list is helical pitch, also known as detector pitch, which is less commonly used, and beam pitched, which is the preferred route to determine helical pitch. Beam pitch is determined from table travel in millimeters per rotation and beam width. Beam width is determined from the number of slices or detectors used and slice thickness. Now at a pitch equal to 1, each detector will record data from one full rotation of the X-ray tube. Pitches greater than 1 means there's an undersampling of data, and pitches less than 1 means there's an overlap in data. What does this mean? Well, if you increase the pitch, you're going to increase the scan speed, but you'll also increase the noise and helical streak artifact. This lowers the radiation dose, but it's also going to lower the image quality. If you decrease pitch, you're going to decrease the scan speed, noise, and helical streak. Comes a higher radiation dose, but you're also going to increase your image quality. Let's talk about field of view. Field of view affects voxel size and spatial resolution. Let's look at the image. Look at the picture on the bottom. CT has a standard matrix of 512 by 512 pixels. You learned this in your earlier CT course. A field of view of 25 centimeters, which is a small field of view, is 250 millimeters. It means that the pixel size in the X and Y dimensions would equal 0.5 millimeters. Now, remember the goal in MDCT is an isotropic voxel, which that would mean that the z-axis resolution would also have to be 0.5. Well, that's all well and good, but what does that mean? Well, the z-axis is slice thickness. So that's what we would be setting, a slice thickness of 0.5. Now looking at the top image with a larger field of view of 50 centimeters or 500 millimeters, the pixel size increases to 1.0 millimeters. So an isotropic voxel would only require 1 millimeter slice thickness. This fact is incorporated into protocol design. The field of view chosen should always be as small as possible to accommodate the anatomy of interest. The corresponding slice thickness should also be used to maximize resolution. Rotation time with MDCT has had improvements. And we're talking about the tube rotation time, the gantry rotation time. There are shorter examination times. Rotation times of a half a second are now routine. There's been a reduction in motion from peristaltic and pulsation artifacts. And there's been better visualization of a rapid dynamic contrast bolus. Now the things that we need to remember that rotation time affects is radiation dose and noise. A faster rotation time will decrease radiation, but it's going to increase noise, thereby decreasing the quality of your image. Rotation time has mechanically reached its peak, and future advances in this area will come from the software developed. An important factor that we need to remember are the radiation dose parameters. This has been in the